Design, development, and implementation of a UAV flight controller based on a state machine approach using a FPGA embedded system by Monterose, Montoya, Jarquin, Braun, presented by Matthew Diedrich. UAVs, or drones as they are commonly known, are aircrafts which can be controlled remotely or fly autonomously. These devices have become very popular in recent years and can be used for several applications. Their article presents the development of a fixed-wing UAV flight controller using a complete parallelism embedded system as a FPGA. The FPGA provides enough power of calculation to extend the intelligence of the system with more autonomy, excellent synchronism, and improved response time. The flight controller is based on a state machine system that migrates from state to state depending on the stimulus received from sensors like accelerometers, tachometers, compass, PIDA, and GPS. The capability and autonomy of UAVs are proportional to the power of calculation of the flight control system. These systems give judgment and guidance to the UAV. The more complex these systems become, the more independent from human control the aircraft becomes. Many solutions for UAVs flight controllers are based on embedded sequential systems. However, these systems are not perfect. The greater number of processes and tasks becoming executed simultaneously, the more variables such as precision, speed of response, and synchronism may suffer. Our proposed flight controller solves this problem because it is based on a concurrent system and can therefore execute many processes at the same time. A top-down design methodology was used for the conceptual design of the aircraft. With this methodology, the full operation of the system can be described. Later, the system's design is divided in block units that can be worked and tested individually. This reduces debugging, prototyping, and integration time. UAV's development is divided into the following 4 areas: propulsion and fuselage, energy generation, telecommunication and video, and flight control system. The goal of the flight control system is to help the user with automatic consumption in all the maneuvers of the aircraft in case of any disturbance. The inputs of the system are the signals delivered to the RF receiver, which delivers the commands coming from the user, and the sensor signals, which give the direction and position of the aircraft in real time. The outputs are connected to the actuators of the aircraft and to the emergency system. The user and the UAV will communicate through RF. The UAV will follow the commands sent by the user, and the telemetry will provide the user important information such as position, latitude, speed, etc. All incoming and outgoing data use a unique communication protocol. The design block units are the sensor block, which is the function to indicate the flight control system about the condition of the aircraft. The data provided by sensors allows the controller to make the necessary adjustments in order to maintain the UAV in its route and detect possible malfunction and hazard. The sensor driver, this block, receives the data from the sensors and sends it to the CPU and the RAM memory to be stored. Most of these sensors are connected to an ATmega processor, which receives the incoming data and sends it to the sensor driver unit. The CPU block controls the route of the aircraft according to the incoming commands from land. Besides transferring all the incoming commands to actuators, it makes all the necessary compensations to maintain the aircraft en route regardless of any disturbance, turbulence, and gusts of wind. The RAM memory stores telemetry data. This data are sent by the UAV's transmitter so that the user can receive real-time information of the current aircraft conditions. The emergency system is in charge of detecting any event that could jeopardize the integrity of the aircraft and reacts executing a protocol where a parachute is released in order to help the UAV land safely. The PWM driver translates the binary data coming from the CPU equivalent PWM signals. These signals control the servo motor's position and the brushless motor speed, depending on the signal duty cycle. The UAV contains the following sensors. Accelerometer dictates the current position of the aircraft regarding to pitch, yaw, and roll axis. The airspeed sensor indicates the speed of the aircraft regarding airspeed. A barometer provides the current altitude of the UAV regarding sea level. A GPS provides the coordinates of latitude and longitude of the location of the aircraft in a map. The compass used for navigation and orientation shows the direction of the aircraft regarding the cardinal points. The tachometer provides the revolutions per minute of the brushless motor in order to make the necessary compensations. The battery level sensor shows the remaining power in the battery, and the radio frequency sensor will send an alarm in case the radio controller signal is saturated with noise, out of synchrony, or low power. The emergency system alarms that trigger the emergency protocol are the following: signal loss, lack of synchrony and RF signal, noisy signal, critical speed, critical battery level, and activated by user. If an emergency condition is detected, a 3-second timer is activated to allow the condition to subside. If not, a flag is set on control unit and the state transitions to the emergency state. The emergency sequence is brushless motors are turned off, the servo motors are turned back to the neutral position, the 3-second timer is activated, then the parachute releasing mechanism is activated, and finally all servo motors are turned off. The finite state machine approach. A finite state machine was needed in order to describe an abstract machine that represents all the possible conditions of the controller and its proper actions. This machine is in one state at a time. This state is known as the current state and can make a transition into another state immediately after a previously defined condition change. The CPU starts with an initial state and monitors the input variables that can change the current state. These variables are set by the radio controller with the data from the sensors and the commands from the user. Each state sets the UAV in the desired course and compensates the actuators. The UAV states are as follows. There's a takeoff state, a climb state, descent, turn right, turn left, climb right, climb left, descent right, descent left, fixed speed cruise, changeable speed cruise, and the emergency state. The hardware implementation. A FPGA is a concurrent embedded system was used to develop the flight controller system. The programming of this device was made possible with the FHDL language. Advantages of FPGA and FDHL are there's a short prototyping time and code portability. It can handle multiple simultaneous processes, and there's a low response time due to the FPGA's internal clock speed of 100 MHz. The FPGA used for the system is an RTX-7 from Xilinx, and it features an on-chip analog to digital converter. It's programmable over JTAG and Flash. It has a 256 megabytes of DDR3 and a 16-bit bus. It has 16 megabits of Flash, and it has Ethernet capability. The response time of the sensors is relatively high compared to the speed of the FPGA. For this reason, a sequential Atmega processor was used to read the telemetry data. A sensor integration program first executes reading functions for each sensor and stores the data in independent variables. Then the communication between the Atmega and the FPGA begins loading all the data in the processor's port B with a 4-bit address to differentiate which sensor the data belongs to. Lastly, an enabler is activated to synchronize the moment when the FPGA reads the data. Thoughts and concerns. I believe the authors outlined a good design for an FPGA concurrent flight control system, but failed to describe its integration with the other systems in the UAV. A major issue in their proposed flight control system, I believe, lies within the flight control system. Their system monitors for emergency conditions from sensor data. If a condition is detected, a 3-second timer is set to allow the condition to go back to normal state, and if not, all motors are killed and a parachute is launched to safely land the UAV. This approach seems excessive, and a more intelligent approach seems feasible. If signal is lost, many dead reckoning algorithms exist to estimate the vehicle's position based on the vehicle speed, acceleration, and orientation when the signal is lost, and could be used to allow for a period of time to attempt to regain signal, if not allow the vehicle to land at a preset set of coordinates. The writers comment they will outline how the UFCS will take into consideration other areas of the UAV system, such as radio controller and power generation systems, but mention very little on how the systems actually integrate together. Another potential concern is the communication between the sensor, processor, and the FPGA. The author references the signals are read and output on an enabler signal, but does not remark on how the sensor outputs are synchronized. Each sensor may take a unique amount of time to output its data, so many sensors may not have output when the enabler signal occurs. So some variety of synchronization must ensue to allow all signals to be output.